Okay, so welcome everyone again, and thank you for being here with us. So, as I was saying, this is the first lecture of our seminar series on architecture and the built environment. And you can see here on the screen, we have a set of distinguished lecturers from different places in the world, which are going to be talking to us about the latest developments in research across architecture, built environment, digitalization, sustainability, a host of different issues there, which I hope would be really useful for everyone. So the one thing in terms of asking questions, so the rules will, if you want to ask any questions during the presentations, please use either the chat button or the Q&A button that you see on your screens. Otherwise, we will have some time, hopefully, at the end of the presentation for some questions, and you're welcome to open your microphones and share your screens and ask the questions so we can have a bit of a more lively discussion, right? So we can do either or. I suppose we'll take all the questions at the end to make the flow of the presentation run better. So today's lecture is entitled Digital Twinning in the Built Environment, and it's a great honor to welcome Professor Ioannis Brilakis from the University of Cambridge that has very kindly agreed to share his time and share some of his knowledge and experience in research on that area with us today. So Ioannis is the Langor Professor of Civil and Information Engineering and the Director of the Construction Information Technology Laboratory at the Division of Civil Engineering in the Department of Engineering at the University of Cambridge here in the UK. So he's completed his PhD at the University of Illinois Urbana-Champaign in 2005. He's then had some posts at the University of Michigan and then the Georgia Tech University in the USA. And he moved to Cambridge in 2012 and has been there ever since. He's, of course, published quite widely, extensively, and he's one of the lead founders of the European Council of Computing and in Construction. So it's a great honor, really, to have you with us today, Ioannis, and we'll pass the floor on to you. So if Mohan, if you just stop sharing the screen, and then Ioannis can share his. And thank you again, everyone, for joining us today.
All right. Thank you, Patricia and Mohan, for inviting me. I will now go back to sharing my slides. The focus of what I have for everyone today is around these two sets of keywords. One is built environment. What do we mean by that, and what's the scope? I'll very briefly mention that. And the bigger thing is digital twinning. What do we mean by that within that context, and why should we bother about it? So before I go into that, just a few things about the place I work in. I don't know if you ever visited the University of Cambridge. It's a very nice location that has a lot of tourists arriving every single day, the whole year, coming to see our colleges like Corpus Christi at the top and King's and Trinity at the bottom. The example I have here for Trinity shows at the front entrance the location of Isaac Newton's office. That's the window you see in the back. And then in front of that is a descendant of Isaac Newton's apple tree. So it's a very popular destination for students to take pictures at. Now, speaking of Isaac Newton, the university has had many notable alumni in terms of mathematicians, scientists, philosophers, and heads of state, such as Niels Bohr and Alan Turing and George Stokes and John Maynard Keynes and our recently departed Stephen Hawking and our current king and many other individuals you might recognize in those pictures. Moving on to something less exciting, the work that I'm about to present to you happens in this location called the Civil Engineering Building. And this looks like a generic picture I could have picked up online from anywhere in the world. which kind of shows how architecture is converging these days across the world, and these buildings can just be anywhere. So the building is not the interesting fact. What happens in it, I think, is the interesting fact. So jumping straight through it, built environment, what do we mean by that? We're referring to three things: economic infrastructure, roads, tunnels, bridges, rail, dam, and so on; social infrastructure, housing, hospitals, schools, prisons, and all that; and of course, the interface of all these with the natural environment. Going on to the other term, digital twinning, there's loads and loads of reports that have come out over the years talking about how digital transformation has taken center stage within the industry, how industry leaders expect disruption to occur at any point in time, and not just the disruption will happen in the digital space, but it's about to happen now. This is not a future change. This is a change that we are already inside. And of course, the lockdowns worked as a digital transformation catalyst because it allowed us to pick up on that pace of change and allow for people to do things digitally that they couldn't exactly or not entirely do before, or they were not allowed to do before. So that was a very useful side effect of the very unfortunate fact that we all had to be in lockdowns. Now, within that space, digital twins are at the core of this transformation, and that's because of the promise. Digital twins promise us better information management. And if I can manage information better, then I can do better across all key performance indicators. I can perform better in terms of cost, time, quality, safety, sustainability, resilience, and every other indicator. However, this is all quite conceptual. And the reality of digital twins is that if I was to ask each and every one of you, what do we really mean by one? I would probably get a slightly different definition. We're still in the early days on this path. So what I did is I started working with colleagues to try to get to the bottom of what is a digital twin, and also what might a digital twin be 20 years from now. What is the future? What is the potential? And we started from a very philosophical place. Imagine a 1-year-old child learning how to walk. They take the wrong step, and as a result of that, they fall down. Well, that provides some signal to their brain. One signal is, ouch, this was painful. And second signal is, I didn't get to my destination as I was planning. So that is then modeled into information, saying that these were probably wrong decisions, that I put my foot there. So that moves us into the forecasting phase, where we start thinking, well, what might happen differently next time if instead of putting my foot here, I put it there? And through that process of planning all these options in our heads, letting the bad options die, and then acting on the most viable one, hopefully we make a better step next time. This is how we walk. This is how we tie our shoes. This is how we drive. This is how we do just about anything. We have this physical manifestation, the body and its actions, and the mental manifestation in the brain, all these activities working seamlessly to allow us to operate. Now, you would say that that solves the problem, but it only solves the problem for tasks that are simple enough, where the entire process of modeling and prediction can happen within our heads effectively. That is not true for a construction project. That is not true for an infrastructure site, because the amount of complexity there is way too big to be able to be planned synchronously and simultaneously within the brain of one individual. And this is where computers come along. And this is where digitization comes along, where rather than physically monitoring with the sensors on our faces, our eyes and ears, the site, we now use other sensors, cameras, acoustic sensors, others, to capture that data on the site and then send that on to a computer in the back office, where we have the planned asset, where this is interpreted into information and into knowledge. And then based on that knowledge, we can start predicting, simulating, making decisions, and through those decisions, providing instructions back to the site so that we can act manually or via robotics and automation, and then create an impact as a result of that, which can then be monitored again, and so on and so on. Have I told you anything new so far? No. You should already know this. This is not rocket science. Perhaps the first new bit I'm about to tell you is, what do we mean by digital twins in this space? In this figure, the circle on the left, I hope you will agree with me, is the physical twin. The circle on the right is the digital twin. So then what is the whole package? The whole package is not the digital twin, unlike some might say. The whole package is what we call a twin system. Okay, two twins working together in a system format, one feeding off the other. So important to nail on these definitions: physical twin, digital twin, and twin system for the combination of the two. Right, so now we've covered that, let's explain a few more things. Why do we need digital twins and twin systems? Well, that's because digital twins have the ability to allow us to increase automation to manage the increasing asset complexity. The way we used to construct assets 100 years ago was significantly simpler, with significantly simpler assets than the ones we have now. We do more because we can do more, and we get more value out of a much more nuanced and sophisticated asset. However, that also makes it very expensive to build, and this is where automation comes along. Why digital twins also applies, because digital twins allow us to combine product and process. They allow us to combine the modeling, the simulation, and the monitoring in the same place. And as a result of that, digital twins are complex and therefore expensive to design, construct, maintain, and operate. But on the counterpart, they are rich, therefore valuable and flexible, able to serve multiple purposes. I work with many companies these days to build digital twins, and we always build them not only for known use cases, but also for the potential future unknown use case. We want to allow extensibility. Digital twins are also federated, and that's because we've left the train long time ago where all the information could sit within one model. Now we link databases together. We allow the information to be queried from multiple places as something of a greater value. And I did mention accessibility already as an example, but I want to point also to a future-proofing example here. Think of, for example, automobiles today. You probably already know that Tesla is not a car company, it's a data company. They're not making cars, they're making computers that happen to have wheels. Most of the cars that are now coming on to the market are mostly computers and sensors on wheels. As a result of that, the life cycle of a car has been reduced to match the life cycle of a computer. See, back in the, I would say, 1980s, 1990s, you'd expect a car to last 15, 20 years. These days, these cars are not designed to last that long because they are technologically outdated in 5 or 6 years. So they're only designed to operate primarily within their warranty period. Can we do the same for infrastructure? The answer is probably no, not if we want to be sustainable. We're not going to build assets like the Thames Tideway, a huge concrete tunnel that's meant to last 200 years. We're not going to cut back on that life cycle a lot. We want it to stay there forever. But as a result of that, we cannot treat it like a computer. We cannot embed it with sensors and instrument it, because those things are not going to last 5 years, and we don't then have an answer what to do the other 195 years. So there's a big mismatch there between the life cycle of technology and the life cycle of the assets we work with. And the last but not least I have here is scalability. And I mentioned before the ability to scale our models to allow for much more functionality in the future, exactly because of the pace of technology. Now, at the end of the day, why do we want digital twins? The short answer is better decisions faster. Faster refresh rate, so therefore more trust in the information. The ability to serve multiple processes, and also more automation, effectively pushing all the low-level decisions to the subconscious, let the digital twin manage that. Think of autonomous driving, it's all low-level decisions, and leaving the high-level decisions to the humans. So if digital twins are so amazing, then why aren't they as ubiquitous as physical twins? Well, there's several reasons for that. The first is that we know the physical twin as a product and process, but we're still discovering the digital twin as a product and process, and we need to do loads of R&D to answer those questions. Also, owners understand the value of a physical twin, but not so much the value of a digital twin. And that's why we need real use cases to achieve rapid market penetration. And last but not least, vendors are presenting incremental solutions as groundbreaking by simply enhancing current products and relabeling them into a digital twin. And in doing so, they accelerate digital twins into the trough of disillusionment. So to get around these issues, I worked with several colleagues, Professor Raphael Sachs and others, to create the figure that you see here, and several others, to help us understand the potential of a digital twin. In other words, not what it is today, but what might it be 20 years from now, as a guide, as a roadmap to success. And so this particular figure takes the assumption that you are something like, imagine yourself standing in front of a lake. What is on the positive axis is the physical twin. What is on the negative axis is your reflection on the lake, the digital twin. And on the physical side, you have the physical product and process as a result. And on the negative axis, you have information volume. So as you go over time, design starts at conception, design and planning. On the physical end, you have loads of designing and planning processes that produce design phase product and process information. And this is what we will call the design phase digital twin, or the fetal digital twin, the unborn. That just told you that the digital twin comes first, before the physical twin. Then you have prefabrication starting, that's the birth, with loads of construction processes kicking off and prefabricated parts coming along. Eventually, we reach the weaning phase, where you leave the mothership, you go to site, and you start installing. And then your child physical twin starts appearing, growing from nothing into an adult physical twin, which happens at project handover, at maturation phase. Throughout the whole process, we are producing construction phase product and process information. And as a result, in the operation phase, we are producing operation phase product and process information. Now, what do we notice in this figure? One thing we notice is that the information side never stops growing. The second thing we notice is that the information side is dynamic. Over time, we have more and more information accumulating, all of which is interesting. The digital twin is therefore a dynamic model over time rather than a series of multiple static models. This is in fact one of the big differences with building information modeling. See, BIM is really this little yellow line you see there. BIM is typically defined as the S-designed, basically product information. And if you're very lucky, you might have a design status model with the design phase process information, or perhaps an S-built building information model with construction phase product information, or a project status model with construction phase process information. All of these static models, and in most cases, not actually talking to each other, not able to query each other's data. There is some recent work in industry about how we bring this together with tools like Quadri, Agave, and others that actually bring them together. But even that is not quite there. Where we want to be is here, right? The entire asset from conception up to whatever is the current timestamp, with every piece of information on a timescale. The reason we want that is that the strongest benefit of a digital twin is that, unlike the physical twin, which does not have the ability to move in time, the digital twin can. The digital twin can go back in time by doing forensics to understand why something went wrong by looking at the past. And also the digital twin can do forecasting, looking into the future. Remember what we said earlier, investigating all the options, letting the bad options die to allow the best ones to come forward and allow us to make good decisions. That's why we need that. Some other fundamentals behind digital twins is that digital twins are made of information, not data. Information meaning things that are derived from data, which are then the raw data held separately and deleted after use. And also can then be interpolated to produce information patterns, which is what we call knowledge, and then further extrapolated to produce insight. All of these, information, knowledge, and insight, and how to produce them, are perfect use cases of AI. And that's the importance of AI for digital twins. Beyond that, I'd like to highlight this slide quite a lot. I presume most of you are very familiar with planning, design, construction, maintenance, and operation for the physical twin, for the physical asset. But how many of you understand the same terms in the context of the digital twin? What is digital twin planning? Meaning the process of understanding the scope of a digital twin, not a physical twin, the feasibility of that digital twin, and the costs. We don't have methods to do that. That's an open research field. What do we mean by design of a digital twin? And by that, I'm talking about deriving the digital twin asset class. Think of hospitals, houses, schools, roads, and of course, the appropriate data structures and cloud architectures that can hold them. How can we construct a digital twin? Meaning to populate that class and derive a very specific asset instance. And also, how can we maintain that digital twin and update that instance at varying sampling rates per attribute? But the most important of all is the last one. How can we use it? Because those first four are just cost. They just cost us money. The only thing that gives you value is that last one. And we have a chicken and egg problem here, which is we need good digital twins to create good use cases for operation. But at the same time, we need good use cases to justify creating good digital twins. So what I have in the rest of the slides I have here is several examples, which perhaps we can go through some of them, depending on how much time we have. Just want to check that this session goes all the way to 1 o'clock, so we have a little bit of time to go through examples. And hopefully some time to get any questions you have from us. So
thanks, Ioannis. Yeah.
Within specifically the phase of digital twins construction, the simplest example I can give you to explain constructing a digital twin is I have a physical twin, for example, a bridge. I go there, somehow I scan it and I get its points and pixels and thermals and GPR and other data. And then I use that to automatically detect the objects and put all those textures on top, the RGB, the thermals, the GPR and all that, and then start detecting interesting information on them, for example, condition information. In that space, we've done work in every part of that spectrum. So starting from step one, we've produced methods that can help us very conveniently get our points and pixels. This is one of the early methods called mid-range mobile videogrammetry that leverages the fact that we have very prominent lines and planes within civil infrastructure, and we use those to help the optimization process, the bundle adjustment, with an alternative one we produce called hybrid bundle adjustment. And as a result of that, we're able to produce a point cloud from 25 meters away scanning just with your phone these days with a error that is less than a centimeter. We've then produced the tools to equalize the densities, fix the holes, and give you a point cloud that you can use quite effectively. We've also more recently worked further into this to add multiple other modalities, such as not just RGB, but also near infrared, IMUs, thermals, others in the same sensor system, and allow us to scan any site. In this case, this is a use case on Whiteley's in London, where we walk around, collect all this data, synchronized in space and time. But at the same time, we have the ability to predict accuracy in real time. We can tell you how good your data is while you're scanning. And once you know that your data is in the red space, the accuracy is very low, that gives you a strong hint that you need to go back into a green area to create a loop closure. And as many of these loop closures as you can create will increase the accuracy of your data set. And you can see here the loop closure going from red to green. Suddenly that area all becomes green because the numbers are fixed now. And you'll see another loop closure there, which makes additional areas green because again, the errors are fixed as a result. Long story short, you don't leave the site until you have exactly the performance you need from your sensor. We've then done a lot of work on the second step because let's face it, points and pixels and all that, that's just still raw data. Humans want to work with the models here. And so the step here is how do we go from the raw data to the models? That is a process that is quite more challenging. That's because for every day of scanning, the work that needs to happen in the background to model that into objects is 10 times as much. We also have to work with data sets in this case that can be, multiple tens of billions of points, where we cannot open these with any existing computer. We have to process the data piecewise and then stitch them together. But most importantly, it's a really boring job, modeling pipe after pipe, valve after valve. Now we have the ability to address this a lot better. I have an example here of how big this problem can be. This reactor building, when it was scanned, it was about 40 billion points. It took 10 people 6 months to make one model.
Oh, hi, Albert. It's Colleen from Asua.
Yeah, Colleen. Yeah.
Hello, hi. Do you want? I've responded to obviously your request,
Yes.
and you've come back to say, do you want to order 5?
Thank you for muting. Appreciate that. Right. So what we've done to address this is we started a long time ago with really simple methods, detecting just columns with a webcam and a laptop. Zoom in 10 years later, we're now able to automatically get the model of a bridge from a point cloud without any human intervention in the process. It's important to highlight that we can do it for real assets. No bridge is straight, no bridge deck or pier or other component is straight. They have all kinds of skews and peculiarities. We're able to capture them quite effectively and go basically from the points in the pixels of real assets to the objects space, and then from the objects directly to the model. We've done the same for buildings, although for buildings is a slightly more tricky process because in bridges everything is exposed, whereas in buildings we have to infer what might be behind because the visible data doesn't provide all the information we need. And to do that, we've come up with a process we call the deep structure digital twin that allows us to start from the point cloud of a building. And because we know we have a building, we start hierarchically decomposing it. The first thing we do is we know the building has floors, so we segment out the floors. Our next assumption is that a floor is made out of rooms. So what is a room in a point cloud? It's a big empty blob. We are looking for those big empty blobs, finding the rooms and segmenting them. Once I know I have a room, again, I can make some safe assumptions that there is probably a slab above me, there's a slab below me, there are walls around me, and so on and so on. I think you understand the process of hierarchical decomposition. And in doing that, we can find floors and ceilings, even in the presence of clutter. We can detect the walls and fit the components in there and create the spaces. We've done the same also for industrial facilities. Now, this is the hardest space because here we're talking massive occlusions, a lot of issues with the data. And yet with a deep learning approach to this, we've been able to capture the mechanical components quite effectively. So cylinders, elbows, I-beams, flanges. And we then use the connectivity of the system, of the mechanical system, to create these connected systems and find the missing bits by being able to make relatively safe assumptions of what might be between 2 points or not. The next step I have here is about enriching this digital twin. So we talked about getting the geometry, putting the textures on top. What can we do with that afterwards? Well, for example, we can start capturing defects or other condition problems. We've done this already in an example for bridges, where we're capturing the different types of problems you see there in the bottom left on the textures, measuring them and assigning those measurements as a property to the asset. We've done the same for roads. So as you drive forward with your car, we can use your parking camera to capture the cracks, the patches, the potholes, and other issues, measure them, and then in real time send those measurements to the digital twin of that road when it is available. This is in fact a really old example of work we've done about 10 years ago. Now, these days, this is commercial. If you buy any new Mercedes or JLR or any other car that has these multiple cameras around, they're already doing this, and they're already selling data to national highways and its equivalents around the world. With regards to sensor data, we're modeling the sensors and we're linking the sensor data to the model so you can visualize it and make decisions. This is the whole point of creating a connected twin system, that it's not just two separate twins, but both of them working together. And we have this example here where you have a bridge in Staffordshire that we have created a digital version of. And then we've linked all the sensor data, the fiber optic sensors, to the digital twin, allowing us to visualize the stresses as the bridge is being used in real time. What we want to achieve is to apply this to the whole country. And this is the National Digital Twin Program that we've been involved for some years to allow us to capture every asset in this way, create these models, link them together, and allow us to manage our infrastructure in a connected way. And more recently, I'm now getting involved with the National Digital Twin Program of China, Hong Kong, and other countries who can benefit a lot out of the same type of technology. What can we do with this? Let's say we make these amazing digital twins. How can we extract value? Let me show you some examples of value. So the first example is a project we did with Langeruk. Langeruk is one of the large contractors here in the UK, where we looked at the use case of High Speed 2, when High Speed 2 started, phase 1. And it was interesting to see that that project has about 300 bridges, where all of them have just one thing in common. They're not iconic. They're nothing special. You want to build them on time, on budget, maximum certainty, minimum disruption. And that makes them a fantastic use case for offsite manufacturing. The problem with offsite is that this is not the standard way of delivering bridges. So we had to go back with Langeruk throughout the whole decision-making process of delivering this asset, from the initial route alignment all the way to a delivered bridge. And in doing so, we mapped all the decision points and the informations you need to make each decision. This allowed us to reorient the decisions such that you have the right data you need to make that decision. For example, in the case of DFMA, we brought the choice of crane very early on in the process, because depending on the capacity of the crane, the weight of the components you design will be limited. And that allows you to design something that will fit the construction process. But the second benefit we got from this that was even more important is that this allowed us to understand what are the dependent and independent variables of this problem. And unsurprisingly for a bridge, the control variables, the things you can affect, is really, really small. For these overpasses, everything is governed by the codes of practice and standards. So we only found about 16 control variables that you can really affect. The great thing about that, though, is that then this allowed us to link all this software you see here together into a design automation solution that allows us to go to the client, High Speed 2 or National Highways or any other client, ask them those 16 questions, put the numbers in, click a button, and automatically get a Pareto optimal front of solutions. Before this, our design partner, Tony G, used to take 7 weeks to produce one alternative. Now they can do 30 different alternatives in 2 minutes. Moving on to the construction phase, we've brought the digital twins into the construction site to allow us to do things like progress monitoring, checking what is supposed to be built, which is all the components you see here, versus what is actually built. And by understanding the differences, the missing objects, this allows us to mark components as behind schedule, ahead of schedule, or on schedule, and so on, without any human interaction. Just simply walk through the site with an augmented reality device, and we can do those measurements for you. We've also brought digital twins into the offsite factory. See, this allows us to have the worker you see here click on a screen and say, I'm just about to start creating this rebar cage. And then as he walks around, we can monitor this person's position, create this spaghetti diagram of movement, and link it back to the component, which allows us to get micro productivity information, which is really, really useful in sensitive operations. The other benefit we get out of this is that just by watching this person work, we saw that he was spending 60% of his time or so on measuring and consulting the model. These are not value-adding activities. So instead, what we decided to do is we can just simply put the model right in front of him and let him build the model exactly where it's supposed to build. And in doing so, I don't need a tape measure anymore. I just need to put the bars where I see the virtual bar to be and let the AR system measure on its own whether I've actually placed the bar correctly or not. That's real-time quality control and not even sampling. We can do 100% every single object. We went further with this to see what can we do to assist workers through robotic teleoperation. I don't know how many of you have seen Real Steel, the movie with Hugh Jackman, where he's boxing, but not really. He's pretending to be the boxer. It's the robot that does all the work. When I saw that movie, my first reaction is, why a boxer? Why not a construction worker? Imagine how it would be like if workers could simply pretend to pick up a huge steel beam and carry it around, and instead the robot does the work. I don't need a crane anymore. The robot can just do everything. But to make that possible, you have to establish this teleoperation loop. And I have here a small example of this through a very simple project we did with one of our undergrads, in fact. Just a couple months, what the student designed is this hand tracker application that allows you to capture everything, including the fingers. And in doing so, he can now control this virtual worker in picking up bricks, putting them in place, picking up a spade, putting some mortar on, putting another row of bricks, picking up a hammer, aligning the bricks, and so on and so on. All the things that a bricklayer would do without actually physically interacting with the material. Of course, you can bring digital twins onto the operation and maintenance phase and allow people to compare physical and digital, see the differences, and extract information from the digital while inspecting the physical. Or to bring digital twins of other assets into the office and allow for people to do inspection in an office environment of the physical asset without having to visit it, either in an augmented reality way or in a virtual reality way by visiting the asset in a device like this one. If you ever come to Cambridge, we can put you into that device and you can walk through the model yourself and see all the cracks and the problems. The last example I have for you, and then I'll open it up for questions, is for the case of asset protection. Something I didn't quite know until I learned about this problem is that a bridge gets hit by a truck in the UK every 4 hours. Now, that sounds crazy, but it's true. The reality is that most of these hits are just scrapes. So the top of the truck just scrapes over the underside of the deck. But several of them can be quite serious, can definitely damage the truck, but also sometimes it damages the bridge. And so infrastructure owners like London Underground want to have this information very quickly and be able to react. The existing systems to solve that problem, for example, with 2 poles on each end and a laser beam, and if you cut the laser beam, there is a warning sign, they're deemed to be very expensive. They cost several £100,000, and London Underground simply told us we would rather let the trucks keep hitting. They're not paying for these solutions. This includes their most hit assets. So I think the top 10 most hit bridges of London Underground get hit about once a week. That gives you a sense of the scale of the problem. The challenge we had is, can you do the same, but an order of magnitude cheaper? Then we can afford to buy that solution and install it. And that's what we did. We replaced the whole sensing system with just a single camera placed upstream in traffic, exactly at the overhead plane. So at that point, the overhead plane becomes a line in the view. And by being a line, you can easily see what's above the line. And if there's a vehicle moving, then that's overhead. You can then use the warning sign and an audible alarm, ask them to exit. If they don't exit and they continue and hit the bridge, we use accelerometers to confirm the hit and tie that back to the video. So we can look at the license plate and find out who did this and go back and charge them for creating that hit. You can see how this works in this slide as we're using Harris corners detectors to detect the overhead vehicle. This was a deployment we did close to the Fairlop station in London. Now, everything else I have, I'll just mention very briefly. The examples I presented are all examples in the past. The current examples, we've done a lot of work as we speak recently on projects such as CBIM, that's looking on how to generate geometries, enriching the product, modeling the process, and creating applications of digital twins in the environment. Projects like BIM2Twin that help us create the digital twin itself as a data structure and then linking a number of different processes to it. Projects like the very unfortunately named Omicron, which we came up before the variant came around, that helps us understand how to digitize inspection, feed data into the raw digital twin, and then use that in a decision support tool to bring it back into the asset. And it's an example here of our work on understanding the digital twin architecture for the case of roads. I'll stop with just this one slide, which is where I'm seeing this research going in the future is we will really be focusing a lot on looking at assets as physical versus digital and product versus process, and making significant advancements across these quadrants, but also on the arrows that connect them. For example, on the physical product, we're looking at how can we make existing inert materials of our assets into smart materials, aware of their state and properties, assisting their maintainers and users. Under the physical process, we're looking at how we can leverage automation and robotics to support proactive interventions and enable automated routine maintenance. Under the digital product, we're looking at how can we integrate smart materials data through the robotics into the digital twin and interface it with every other bit of information, knowledge, and insight. And under data science, the digital process part, it's all about leveraging that rich information set in the digital twin to drive that insight to inform design, construction, maintenance, and operations. A lot of our projects are now focusing on this. I'll stop here. Just a quick plug on a book I published that covers quite a lot of these topics on infrastructure computer vision. An acknowledgement to those who actually did the work at the bottom and those who paid for it at the top, and to thank you and ask for any questions you might have.
Ioannis, thank you so much. I know you can't hear the people here, but anyway, thank you so much. This has been an absolutely fantastic, wonderful presentation. Thank you for sharing all those examples of current and past research with us. And I think this is a topic which is absolutely fantastic. I'm fascinated with it, and there's more to learn every day. So thank you. Right. We have had a question on the chat here. That was Albert Aduse. Well, Albert, would you like to ask yourself the question, or shall I just read it? Mohan, I think you can try and let Albert speak if you want.
Yeah, thank you. I was just asking, I'm just doing a research on the effect of infrastructure development and innovations on achieving corporate sustainability. And this trend seems to look at what I'm also looking in. So my question is, how can this be implemented to help achieve corporate sustainability in the realms of soft infrastructure development, like looking at the BRIM, the CA for Computer Aid Facilities Management System, capturing the length and other steps? How can this trend help us to also achieve corporate sustainability through soft facilities management system or infrastructure development? I don't know if my question is clear.
I'll try to answer it, and you tell me if I got it right. So we cannot improve something if we cannot measure it, right? And if we want to do sustainability right, we have to have mechanisms by which we can first measure how sustainable we are. We can evaluate different solutions and understand their impact on the environment. And right now, that space is very chaotic. There is tens, possibly hundreds of different carbon calculators out there that don't quite do things in the same way and produce very different results. So it's very hard to create trust in the output of these tools. And this is what, on one end, the sustainability community has to put in a lot of work to standardize those tools so we know what answer we're getting. And companies cannot game the system, or at least not game the system significantly, because there's always going to be a certain amount of latitude in there. And on the other end, what digital can provide is the ability to do that effectively, quickly, present the data in a better way, and then link it with all the other parameters. Because remember, sustainability is very important, but it's not the only thing out there, right? We're looking at cost and time and quality and safety and everything else, and we operate in a multi-objective world. So we need to be able to consider all these parameters at the same time. The only way to do that is in the digital space.
Thank you.
Thank you, Albert, for sharing your screen as well. I think Freya, she's got a question as well. Freya, if you would like to ask your question, maybe share your screen too, if you can.
Yeah, so
thank you.
Yeah, thank you. I guess this could be a bit of an alternative kind of question, because my master's research, it's not focused on architecture. It's I'm designing a platform that allows blind people to produce video games and other kind of content through a very basic programming language. And when focusing on making a kind of code that allows blind people to make interactive soundscapes, I've been able to figure out quite a lot there, because obviously audio is a much more accessible sense for blind people rather than sight. So at the moment, I was trying to figure out the best way to design a platform, or a way in which a blind person could design a landscape, a visual landscape, without seeing it. And I was just wondering if you thought, digital twinning or anything similar to this could be a good start for me to look at.
If you allow me to slightly modify your question, I will try to generalize, because what you hinted on is actually a small part of a much bigger problem, which is how humans interact with data. And your example is one of the categories within that. So the counter example I'm going to bring is that, and it says a lot about our industry today. I visited India a few years ago, the headquarters of Larsen Toubro, and the very first thing they showed us on their campus was a huge building, massive building, that was full of classrooms. And all those classrooms were teaching BIM. And the company was complaining that it takes 2 years for us to teach people how to use these systems, and that's about as long as they stay with us. 2 years later, they've already moved on to another job. So there's huge turnover, and they don't have enough time. By the moment they train someone, they've moved on to something else. But they were still convinced that the solution to the problem was more education, right? We need to educate people to use BIM, otherwise we won't be able to solve the problem. What never crossed their mind is that perhaps the reason people need so much education is because the software is crap.
Right.
Okay? That just never crossed their mind. And this is the case I'm trying to make. The tools we have are not even fit for purpose for people who are not blind, let alone for people who are. We have a huge amount of work to do to copy what, for example, the smartphone industry can do today, where you have a very complicated device that even a 1-year-old can pick up and start using, right? This is called complexity encapsulation. Hiding the things that are non-value adding to the user and presenting the things that are value adding to them individually, and allowing the same device to be equally useful to anyone from 1-year-old to 99-year-old, even though they're looking for completely different things around, all these different ages. That's one dimension. Another dimension is the disability dimension. Having tools that can help, that can be useful both for people that have, they're blind or hearing impaired, or all these different scenarios, and still having the ability to use the same systems. So if you're asking for how you can do that, the best direction I can point you towards is look at the smartphone community. What have they done for those who are hearing impaired or blind or other categories? How are they approaching the problem? And how did they design their solutions? Perhaps we can learn from that and do at least as good as they have.
Right. Okay, thank you.
Thank you. We'll take a final question. We just have 2 minutes here, but we'll take a final question from Shikar, which is on the screen. I'll just ask you the question, I think, in the interest of time, Ioannis. So he's asking about the benefits achieved by implementing digital twins in design coordination of complex projects such as hospitals, and what are the limitations and disadvantages? I think this is more about BIM rather than digital twins, if I understood the question correctly, but go on, please.
To me, that sounds like a very good research problem. I think you've nailed it. That's what you need to focus on if you want to do a research project. Do we have clear answers? We don't. And this is why we do need to do research. But also, when we say digital twins, what do we mean by that? Right? Are we looking at a static model like a BIM file and how that can be used? Or are we looking at a dynamic model, like a digital twin that can do forensics, go back in time, and forecasting, look forward in time and make predictions within the same environment? We are rapidly evolving in this space. We're rapidly creating now these new tool sets. And I think that will create a constant need for change. So we need to change now. We will again need to change 2 years from now, and 4 and 6 and so on. And the human factors component is super important, because as the technology pace is accelerating, the need for constant change will accelerate. Therefore, we really need to find ways to make that change happen productively. Otherwise, people will lose the train. And if they lose the train, it's very hard to get them back on, because technological pace will keep going.
Absolutely. Thank you. Thank you, Ioannis. Thank you so much. I think this has been an absolutely fantastic session. Thank you, Ioannis, for your time. Thank you for coming over here today virtually and sharing all these wonderful examples and all this knowledge with us. Just for everyone else, just to say that our next session is going to be on the 4th of October next week, and it's going to be Professor Song Woo from Nottingham Trent University here in the UK as well. And the subject matter is a little similar as well. So Song has done a lot of research around digital technologies, and the title of his presentation will be From Eyes to Lens, a Journey Towards Digital Bridge Examination. So there will be some links with what was presented today, I'm sure. So, Ioannis, thank you very much again. Thanks everybody for being here with us today. Hope you enjoyed it, and I'll see you soon. Thanks, Ioannis.